And, oh yeah, I restarted, so I don't even have my slides open. There we go. I feel like I've learned how to maneuver through Zoom so quickly, and I will probably never use these skills again. Thank goodness, though. Let's see. So last Wednesday, we talked about ether reactions and epoxide reactions. And so today we're going to start with thiols and sulfides. I don't think we'll take the full time for lecture today either, which I kind of, well, I don't know if you remember, but last week I said I was trying to get through more than half last week. So that today's lecture wouldn't be as heavy. But we'll see. We'll see what happens. Sometimes I've planned for them to be short and we end up talking and asking a bunch of questions and they go a little longer, and that's okay. All right, so we are starting with thiols. Well, let me take a step back for a sec. Sulfurs and oxygens are super similar. They're in the same column on the periodic table, so they both have 6 valence electrons. They both are going to form a -2 charge if it's just that atom by itself or that ion by itself. And so the way that they bond is very similar. And so they both form an ether type compound where it's either an oxygen or a sulfur in the middle and then carbons on either side. And then they both form an alcohol like compound where it's a sulfur or an oxygen with a hydrogen attached and then a carbon on the other side. So when it's an oxygen, we of course call them alcohols. When it's a sulfur, we call it a thiol. So the OL part is kind of the alcohol part of the name. And then thio, I'm not sure if that's a Latin thing or not, but that prefix gets used with sulfurs a lot. So if you see that in other classes, you see that thio, you know that there's some type of sulfur involved. This is another one that has an old name that sticks around. They're also called mercaptans. I don't know. Latin, I'm sure, something, but it's definitely an old name that is stuck around. They are very stinky. Sulfur-based things tend to have kind of a skunky smell to them or a fishy smell, depending on how many carbons there are, but usually stinky. The way that we name these, we have 2 different ways. If our thiol is part of our parent chain, then we literally just end it with thiol. So over here, 1, 2, 3, 4. So we have a 3-methyl, 1-butane thiol. So it's a little bit different than how we've added on suffixes for other ones. So if this was an alcohol, we'd say butanol. We'd get rid of the E. The reason we keep the E here and we say butane thiol is because it's an N and a T. And so we don't have 2 consonants in a row. We leave the E in there. So it's really just more of like English rules and not chemistry rules that we're following for that. So if you left the E off and called it butanethiol, I would not mark you down because it still gets the point across. Sulfurs go pretty low on our priority list in terms of our functional groups. And so if we have another functional group, which really the only other one we've really learned how to name are alcohols. If we have an alcohol on our chain as well, then we call our SH group, we call our thiol a mercapto. So here's the compound right here. We have a methyl group attached to carbon number 3. We have an alcohol in number 1. So just that portion, we have 3-methyl, 1-butanol. That sulfur group on carbon number 3 becomes 3-mercapto. So it's just what we call it as a substituent. We'll do a couple practice naming ones on the next slide. A little bit more on property stuff. It's a strong nucleophile. It's a weak base. It's good at SN2 reactions. So we've seen this back in chapter 7. Sulfur is not as common as other ones, but it is really good at being a nucleophile. So we do see it show up occasionally. It's a good one to use in examples because it is a little bit different. and it is good at its job. So let's do a couple practice ones here with some thiols. We'll do that. We'll keep them a little simple, but add in some stereochemistry. Oh, I made that first one a little tricky because of numbering. I didn't mean to, but I totally did. Because of course my first question is going to be, where do we start numbering that top structure? We are going to start numbering it on the right. So 1, 2, 3, 4, 5, 6. And we have our methyl up there. We have this new guy right here. We're going to start numbering it on the right because the sulfur does take priority over the alkene. I will double check to make sure I didn't put any on the test like this because that's not a rule you really need to know right now, but it is a rule. So we know that it's a hexane. Well, not quite a hexane. We have a double bond in there. We know it's a hex. We know it has a methyl. We know it has our new SH group. What are we going to start with alphabetically? Who gets to come first? The methyl. Perfect. So we're going to say 3-methyl. 2. That is not a 2. I said 2. Did not write a 2. 2. No, not 2. Sorry, I'm skipping a bunch of things there. 3-methyl. Let's start there. Parent chain. The rest of it's parent chain. So I'm going to leave some space here for some numbers. Our numbers will go right there. We'll fill those in. We know it's hex because there's 6 carbons. What's that full name going to be for the parent chain, though?
Hex and thiol? I don't know.
Yeah, exactly. So hexene thiol or hexenthiol. Yeah. So we have the double bond. So we have to say that the ene part. So if we kind of dissect the name, that tells us that there's 6 carbons. That tells us there's a double bond. And that tells us that we have our new thiol. So if we put in our numbers, our hexene is at carbon number 4 and our thiol is at carbon number 2. So I'm going to erase my little bracket right there. But we would just say 4, 2, hexenthiol. And again, we can separate those out like we've done with other names. So I'm just going to erase the circle just to give me some space here. But we could put hex 4 ene 2 thiol or 4 hexene 2 thiol. Both of those or all 3 of those would be completely correct. Any of them work? Any question? Oh, you know what did we forget? We forgot that stereochemistry. I put it in there on purpose. Totally forgot it. We're going to put little parentheses there. We do need the number. Give myself bigger parentheses. 2. So we're going to have to say 2R or 2S. And the reason why we need the number is because carbon number 3 is a stereocenter. We don't have a dash or a wedge there, so we don't know if it's R or S, but it is a stereocenter. So because there's more than one stereocenter, we need the number to go with it. What is number 2? Is it R or S? I agree. And let's see, I need to make these parentheses. We're just going to put the parentheses up here. We're going to say 2R, and it's R because the sulfur would be the highest priority, and then the longer chain would be second, and there's our third. So 1, 2, 3, and we're going to the right, so we get the R. And then our double bond. For our double bond, we can say trans because we have the 2 hydrogens, so we can compare the hydrogens to say whether it's cis or trans. We could also say E, but there's our full name, 2R trans 3-methyl 4,2-hexene thiol. We don't need a number in front of the trans. We don't need to say 4 trans because there's only one double bond in the structure. So we wouldn't get confused as to which part gets that label. There's only one thing that can have that label. Okay, now that we've given it a full name, any questions about that one? Okay. Second one. Do you think we're going to start numbering this at the alcohol or the thiol? Yeah, so at the alcohol. So we're going to start numbering at the alcohol because the alcohol becomes part of the parent chain name, and the thiol is going to be a substituent in the front. And so because the alcohol is part of the parent chain name, it gets higher priority. So we're going to say 1, 2, 3. So 3 mercapto. And then 1, what's the name of our parent chain for this?
Cyclohexanol.
Perfect. Can I fit it all in there? Barely. Because the alcohol is on carbon number 1, putting in that number 1 is actually optional. So we could just say 3 mercapto cyclohexanol. And because a number isn't given for that alcohol placement, it would be assumed that it's on carbon number 1. We do need a little bit of stereochemistry in there. What should we put in the very front of this to give it some stereochemistry? There's 2 ways we could actually label this for stereochemistry. One's an easy way and one's a hard way. What's the easy way? Do you see it?
R.
Oh, sorry, I skipped slides on us. So we could figure out R's and S's. That's the hard way. So 1, 2, 3. This one would be R. Are they both R?
Yes.
1, 2, 3. 1, 2, 3. They are. So okay, here's how we could label it the hard way. We could say 1R, 3R, and then the full name. What's the other way that we could label this one that does not require R's and S's? So not E and Z, but you're getting close. So E and Z is just for double bonds. What's the other prefixes we can use though?
Cis and trans.
Yeah, cis and trans. So which one would we use for this? Would we use cis or trans?
Trans.
Perfect. So we could use either one of these labels, trans or 1R, 3R. Both would be correct. We can only use trans with rings if there's 2 substituents. If there's 1 substituent, 3, 4, 5, none of those work. It only works if there's 2. And so that's why I say this one's easier, because all we're doing is saying, okay, there's 1 dash and 1 wedge. That makes it trans. So a question in the chat asks, why is it mercapto? So I'm gonna go back 1 slide to answer your question. When our thiol is the only functional group on the chain, it gets to be thiol. It gets to be part of that parent chain name. But when there's another functional group on the chain, then the thiol gets demoted. It has to become a substituent instead of a functional group, and we call it mercapto. So it goes to a substituent portion of the name instead of a parent chain. I don't know why it's actually called mercapto, but that's what we call it. And you're welcome. Any other naming questions?
I had a quick question for the mercapto.
Yeah.
If you have other substituents, are you just doing alpha order, or like that doesn't have like a higher? Okay.
Yeah, we're just doing alpha order. Yeah.
Thank you.
Yeah, the epoxy one that we talked about, off the top of my head, I think that's the only weird one that kind of breaks that rule. Any other questions on that? Okay, then let's look at a couple reactions. So just like other stuff, we talk about how to make them first, and then we talk about how to react them. So reaction number 9, preparing thiols. Oh, I'm gonna fix my typo. Via substitution. So this is stuff we know. This is chapter 7 reactions here. If we are using a primary methyl or secondary carbon, we can do an SN2 reaction. So we're starting with our alkyl halide, methyl, primary, secondary. We're reacting it with NaSH. We've seen this before. We don't care about that sodium. This is really just an SH ion. And we will make our thiol. This is an SN2 reaction. Just trying to decide where to write this. We'll go over here. And so notice in the second one, we're going to get that inverted stereochemistry. So if we're starting with primary methyl, there's not going to be a stereocenter because there'll be too many hydrogens attached. But if we're starting with a secondary carbon, it could be a stereocenter. And so in that case, the stereochemistry would be inverted. There's no carbocation intermediate when we do an SN2 reaction, so there won't be a carbocation rearrangement that we have to worry about. So really no regiochemistry. It's only going to react at the alpha carbon, or the carbon where the leaving group is attached. So again, though, this is chapter 7. We've seen this, and we've seen it repeated a lot, but specifically looking at it with sulfurs. All right, one more way to, oh no, I think this is our only way to make them, I believe. It sure is. Okay, this is it. This is the only way we have to make them. So doing substitution reactions. Any questions about this reaction? Okay, so we have a couple reactions. I'm looking at my notes here. I think 2 reactions to react them, and then we're going to switch over to the sulfides. So the first one is to make a disulfide bond. So this is reaction number 10. So we're taking 2 thiols. We're reacting them with hydroxide and water and some bromide. And we make a disulfide. So a disulfide is literally just 2 sulfurs bonded together. So it's kind of like the sulfur version of a peroxide. So a peroxide, remember, is just when we have 2 oxygens bonded together. I am looking strangely at the bottom of my slide because look at the charges on those atoms. They came in as weird symbols instead of charges. That is, I don't know how that happened or why that happened. That is super weird. I will go through and edit those as we talk about it. It totally threw me off though. Okay, so this makes a disulfide. This is something that we see in biochemistry a lot. If you've heard the term like sulfide bridges, so it happens between amino acids in proteins. We make disulfide bridges, and then if you are trying to unravel a protein or denature a protein, you have to break those disulfide bonds, which we'll actually look at on the next slide. But let's look at the mechanism for this one and do a little bit of editing with these super weird charges. So our sulfur ion here, I'm going to just change this over to a negative charge, is going to do a nucleophilic attack on our bromine. So here's our nucleophilic attack and loss of a leaving group. So look at that. Our SN2 mechanism shows up yet again. And then this sodium here, we don't really care about him, but he does have a positive charge. So we'll fill that in. Notice that our thiols are starting this reaction, but right here we're starting with a sulfur ion. So really the first step of this mechanism is with the hydroxide. So we're removing that hydrogen from the sulfur with the hydroxide. It becomes a sulfide ion. And then we can do our attack on the bromine. So now we have this sodium bromine bond. We're going to do another SN2 reaction. So we're going to do a nucleophilic attack, sulfur to sulfur. We lose that bromine. And so here is our disulfide. I will go in there and fix those weird charges. This was totally copy and pasted from the PowerPoint slides that come with the textbook too. So I don't know how that happened, but there we go. So we're doing a back-to-back SN2 reaction. So the bromine is just kind of being used to create a leaving group. So we're using the hydroxide to remove that hydrogen to create a good nucleophile. And then we are bonding to that bromine to make the sulfur into a good electrophile because it has that bromine on there as a leaving group. So in that second step, this bromine, or not bromine, excuse me, this sulfur is our nucleophile. This sulfur is our electrophile because of the bromine that's attached to it. So they can play both roles depending on what kind of environment they're in. We have one sulfur that's negatively charged and one sulfur that's bonded to an electronegative atom. And so they can have both a negative and positive environment depending on what's around them. All right, but we make a disulfide. So we also want to know how to break that apart. So reaction number 11, disulfide cleavage. So we're breaking it down. So here's our disulfide. We're reacting it with hydrochloric acid, some zinc. This is a reduction reaction. That's not a reagent. You don't need to write that on the arrow. It's just telling you what's happening in this reaction. But what we make are 2 thiols. So whether this reaction, or let me rephrase that. Generally, this is going to be symmetrical. We would start with 2 of the same thiols, and then when they bond together, it would create a symmetrical disulfide. And so then when they break apart, we're making 2 of the same thiols again. It's usually that way because it's going to give us one product. If we started with one long thiol and one short thiol, when they bond together, we would just get something that's asymmetric. But we would also bond together 2 long ones and 2 short ones, as well as 1 of each, because we wouldn't be able to control that. And so starting with 2 of the same would give us 1 product, whereas if we started with 2 different ones, we would get 3 different products. So a little side note there. Let me see. I'm looking at my notes here, see if there's anything else. I think that is it. That's it for thiols. Let me draw some boxes here for us. Oh wait, do we want boxes yet? Oh, yeah, we got a spot for boxes. I just had the first question doesn't quite work, but we will just skip that one. One, 2, 3, 4. Had to go long ways there. Okay, so just a couple reactions here. What am I? Oh, I know what I was missing. We will go right here then. Okay. This is a super weird way to do this. Let me just put a little divider line in there. Sorry, I made that messier than I wanted to, but they're there. All right, I'm going to turn on the annotation and turn off our names. There we go. Okay, please feel free to fill in a box with one of our thiol reactions. Looking good so far. I'm going to fill in some reaction numbers here. So this is reaction number 9. So the sodium with the SH attached to it, perfect. So that's creating our thiol. And then to create our disulfide, we have sodium hydroxide, we have bromine. This is reaction number 10. And then, yeah, perfect. HCl and zinc, our last one. So breaking that disulfide bridge apart. Questions at all about the thiol reactions? Okay, beautiful. Okay, here we go.
Professor?
Yeah.
Professor? Yeah, sorry. On the one on top, do we have to put the H2O?
So for this one, you could just put NaOH and Br2. Generally, if there's water in something, or well, if there's like acid or base in something, the water's kind of assumed. So you could put it in there, or if you left it out, it's really kind of assumed that it's in there. If water was our only reagent, then of course we'd have to write it in there. But
okay, so if it's missing, it's not going to be incorrect, right?
that is correct. You would be fine.
Thank you.
Anything else on these? Good question, by the way. It is, I know at this level, it's you're not always sure when things are important or when they're kind of assumed. So you can always ask those questions. All right, last section. We're on to the sulfides. So a sulfide is kind of like a sulfur version of an ether. Because of that, of course, they have another name. They are also called thioethers. So we have that thio prefix in there again. So it's RSR. So just like an ether, but with a sulfur in the middle. When we name these, again, we have two ways to name them. If we have a simple sulfide, we can add in the word sulfide at the end. So this would be alkyl sulfide. So if we had something like that, we would call it ethyl methyl sulfide. So this was very similar to our ether rules. So this is more for a simple or non-branched structure. And then if we have a larger structure that just happens to have a sulfide attached to it, that's where we would treat it as a substituent. So of course we have to say where it's at, that's the number part. And then the name that we give it is whatever the alkyl group is, and then the word thio. So in this structure over here, we have a cyclohexane as our parent chain. We have these 2 chlorines attached. So we have 1,1-dichloro, and then our new group right here is 4, so 1, 2, 3, 4, methyl thio. So methyl because it's a methyl group, thio because there's a sulfur attached there. We put it in parentheses to emphasize the fact that the methyl and the thio go together. So it doesn't look like there's two separate things. It gets alphabetized by whatever comes first in the parentheses. So that's actually a parenthesis rule. So if we have like something, if we have a like a complex branch substituent that needs parentheses, whatever letter comes first, so in this case the M, that's what we're alphabetizing it by. We know that the di doesn't count when we alphabetize, so for this one we're alphabetizing the C in chloro and the M in methyl. So it doesn't necessarily always go up against the parent chain name, just depends on what it is. Numbering wise, this one started at the chlorines because that gives us the smallest numbers. If we were to have started, if we started at the sulfur instead, we would use the number 1 and then 4, 4. But the way that it is numbered, the way that it is numbered, we use 1, 1, 4. And overall, 1, 1, 4 is less than 1, 4, 4. So it doesn't get a higher priority than anything else in terms of numbering it or alphabetizing it. We're just following the same rules we already know. All right, so I'm going to draw one sulfide, and we're just going to name it both ways. So that does mean I need to draw something that's not too branched. I think we'll maybe practice. Or how about we do this? Okay, and that way we're practicing a couple of our common branching names. So we will do, we'll treat the sulfide as our parent chain first. So if we're treating it as our parent chain, we're going to name this substituent and this substituent in alphabetical order, and then the word sulfide. So what is the name of this one? That one's oh, go ahead.
Sec-butyl.
It is sec-butyl. Good. And the name of the other one?
Isopropyl.
It is an isopropyl. Perfect. So sec-butyl, isopropyl sulfide. We've talked about the alphabetizing rules with these, but just as a reminder, we're using the B in butyl. We're using the I in iso for those alphabetizing. Numbery prefixes don't count, so that's why we don't use the sec, just like we wouldn't use tert or di or tri or tetra or any of the ones that sound like numbers, but iso does count. So sec-butyl, isopropyl sulfide. They are 3 separate words. So this happens often when we're doing like more of like the common name version. So when we have with the common names, it has the spaces and it has the 3 different words because we're not using any numbers to say where those different things are at. Okay, questions about that first one? Let me put a little divider line here. All right, so let's treat it as a parent chain then. So if we treat it as a parent chain, we are going to pick our longer chain. So that would be the butyl. Oh, sorry, there's stuff in the chat that I totally missed. Would it be wrong if we said 1 methyl, 1 ethyl instead of sec-butyl? No, so we could do that. So we could call this 1, 2, 3. So that would be 1-methyl-propyl. And then the other side would be 1, 2. So it would be 1-methyl-ethyl. And then we'd still have the word sulfide, of course, which I totally squished in there. We'd have to flip them alphabetically, though. So I'm going to cheat and just do this. Yeah, you could definitely do it that way. I feel like numbering them and naming that way, because they now have substituents within them, it kind of takes away from it being like the simpler naming version, but it is still correct. Okay, I'm going to redraw this just because I have numbers all over it now. The butyl side's the bigger side. So that's going to be our parent chain. So we're just going to say 1, 2, 3, 4. So attached to carbon number 2 is this substituent. So we are going to call this 2. And then in parentheses, we are going to write isopropyl thio. And then we'll talk about the other way to do it as well. Isopropyl thio, and then butane. So the other way, let me give it some more numbers here. We'll say 1, 2. So the other way would be 2, and then in parentheses, oh, I see that my writing is lagging. I wonder if my tablet's getting warm. That does happen when it gets too hot. But I will slow down also. Okay, so if we, instead of calling this isopropyl, if we use it with the complex branching, so the 2 that I've written down right now is for the 2 on the butane. And then attached to that, we would say, again, a second set of parentheses. That does not look like a parenthesis. Let's try that again. There we go. We would say 1-methyl-ethyl thio, and then the word butane. That's definitely not the prettiest of names, but it's correct. So with our sulfide as a substituent, the biggest thing is remembering that it does have to be in parentheses. And when we alphabetize, we're going to use whatever the first letter is. So it would be the first letter of our alkyl group. Questions about either one of those?
Professor Henry, I have a quick question on the previous slide. So for like the naming on the bottom compound, it's only numbered, it's only numbered because it has the lower numbers for like the chloro, correct?
Right. And the chlorine gets the lower numbers, not because it's more important or anything, but because there's 2 of them. So we're going to use that number twice.
Perfect. So if it was a thiol, it would still be numbered the same way?
Yeah.
Okay, got it. Thank you.
Yeah. Any other naming questions? Okay. So obviously there's going to be naming on this test. I think I want to say 4, like 2 where you have to draw and then 2 where you're given the drawing and you have to name it. And essentially we've learned 4 things to name: ethers, epoxides, thiols, and sulfides. So you will get pretty much one of each of them on the test. You'll either have to draw it or you'll have to name it. So they will be on there. Nomenclature ones are usually 3 points each. So Of course, it's worth some points. If nomenclature comes easy to you, hopefully it's easy points. If it's something you struggle with a lot, it is just 3 points. So just kind of keep that in mind, how much time you dedicate to remembering all these little rules. But there you go. There's a little heads up for you. All right. Sulfide reactions. So first, how to make them. So reaction number 12, preparing sulfides. So we're starting with our thiol. And in 2 steps, we're going to react it with some hydroxide. So don't really care about that sodium. And then in the second step, we're reacting it with an alkyl halide. And we make our sulfide. So notice that the alkyl halide has the little tick mark on it. Let me erase my circles because I kind of just crossed it out when I did that. That's, again, to tell us that the 2 R groups aren't the same. So we could make this a symmetrical sulfide by using the same R group, or we could use a different R group and it can be asymmetrical. So either way. Here's our mechanism. Oh, and actually, let me add in a step because we are not showing that first step here. Sorry, need to go up a little, need a little more room. So proton transfer, we're just using that hydroxide to remove that hydrogen off of our sulfur. And then we get our sulfur ion. Again, don't really care about sodium, don't really care about the water, but this is what we get. So in that second step, we're going to use our sulfur to do a nucleophilic attack on our R group, loss of a leaving group. SN2 reaction. So we've actually seen this exact reaction in chapter 7. We've used sulfur as a nucleophile on our alkyl halides before. So we've seen this happen before. Because we are doing an SN2 reaction, our alkyl halide, methyl, primary, secondary. So we do have a little bit of limitations there, but not a whole lot. It's going to work like our SN2 reactions. I'm looking to see if there's anything else. No, the only thing I wrote down was that the first step's not showing on the mechanism. Oh, just a second. My cat is digging in my trash can. Hey, what are you eating over here? Yeah, you don't need to eat that. Just be a good kitty. Just trying to eat old cream cheese stuff in the garbage. Okay. Any questions? Okay. Number 13. So reaction number 13 is an alkylation reaction. So let me write this out a little bit more generically. So because we have the mechanism here. So we'll start it just like this with our sulfide. We are going to react it with a methyl halide and then some other kind of nucleophile. The goal of this reaction isn't anything to do with the sulfur. We still get the sulfide in the end, but our methyl is going to be attached to the nucleophile. So the sulfur is really kind of just acting as a messenger for this reaction. I'm going to give it some labels here. So this is our methyl halide. This is a strong nucleophile, but it can be any of our strong nucleophiles. And now we have a methyl bonded to whatever nucleophile we used. So here's how it happens. Nucleophilic attack from the sulfur onto that methyl group, loss of a leaving group. So SN2 reaction. We have an alkylated sulfide. That sulfur group is a really good leaving group. So the halogen might not have been as good of a leaving group, which is kind of the purpose of doing this. So the sulfur itself is a much better leaving group than the halogen was. So then in comes the second step, our nucleophile. We're going to do another SN2 reaction. So nucleophilic attack, loss of a leaving group. So the sulfur is our leaving group. So the sulfur is untouched. We start with a sulfide, we end with a sulfide. He's just the helper of the reaction. What we end up with, though, is this methyl attached to a nucleophile. So it has to be a methyl with a halogen on it. It can't be anything larger. And the reason for that is because of this step right here. We want the nucleophile to bond to the methyl group and not the R groups that are attached to our sulfur. So it needs to be the least sterically hindered carbon in the structure. And so we don't want it to have anything else attached to it. So this would give us a carbon that's easier to bond to, that's more available. So it's kind of a weird reaction because we're putting it in the sulfur section because we're utilizing the sulfur, but it's not the sulfur that's really the product that we care about. It's this carbon that's bonded to a new nucleophile. Methyl carbons can be a little bit hard to react because they don't have the stability of having like neighboring carbons. So this kind of gives it that neighbor in the middle of the reaction, gives it that sulfur with those other carbons attached to it as kind of stability neighbors so that the nucleophile can come and bond to it. So kind of a weird roundabout reaction to get a carbon with a new nucleophile, but it is a handy reaction. Any questions about this one? I don't think I even put this one on the test, to be honest. I don't remember it being on the study guide. All right, one more reaction. Number 14. So number 14 is oxidation. So there's actually two different reactions that fall on this slide, but both of them start with a sulfide. So these are both shown with benzene rings, but that's definitely not a requirement. I'll use the reaction at the top to fill in some generic stuff, but we're starting with a sulfide. And we're going to do two different oxidation reactions. If we react it with sodium periodate, so NaIO4, we will create a sulfoxide, so a sulfur with a double bonded oxygen. We've seen that name before because we used DMSO as one of our solvents, which is dimethyl sulfoxide. So if there's two methyls attached, if our R groups are methyls, that would be DMSO. And then if we react our sulfide with two equivalents of hydrogen peroxide, it will create a sulfone. So now we have those two R groups attached and two double bonded oxygens. We don't see expanded octets very often in organic chemistry because we don't use larger atoms very often, but because sulfur is in the next row of the periodic table, it can have that expanded octet. So it can have more than 8 electrons. So I'm going to put in 2 times H2O2. And we've talked about this before. Right here, down here, it's just written as 2 H2Os. You might see it written as 2 times or 2 equivalents or 2 moles. They all mean the same thing. It's kind of a preference on how you want to write it. I don't usually just put the number 2. Just, I don't know, I feel like it needs something else in there. But it is correct. It's not wrong. So we can kind of treat this as a continuous reaction going from the sulfide to the sulfoxide to the sulfone. Or if we react our sulfide just with the hydrogen peroxide, it will go directly to the sulfone, which is what's shown down here, going from the sulfide to the sulfone. So the fact that these are shown with benzene rings is really just to show that it's okay to have benzene rings on there, meaning benzene rings don't affect it. Having a bulky group doesn't affect it, but the benzene ring is not a requirement. Let's try that again. It is not a requirement by any means. No mechanism for these ones. It gets a little weird just because there's so much stuff involved and we're using expanded octets. Really no regiochemistry because it's only happening to the sulfur. So not a whole lot of extra info to put on here. No stereo centers because again, it's just happening at the sulfur. So we're not going to have a stereo center there. So this is definitely a flashcard one, meaning not a whole lot of stuff to understand, just kind of a memorizing one. Questions about this one at all?
Yeah, on this one, if this one is on the test, if we put the H2O2, it's gonna be correct, or we have to put both of them, like the NaIO4 and the H2O2?
So those are going to do two different things. So if we're making, okay, do I have a blank? I'm going to just go to a blank slide just to show you. So if we had, these on the test.
Okay.
The top one, so as we're going from our sulfide to our sulfoxide, this would be the NiO4.
NaIO4, yeah.
And then the other one would be the 2H2O2.
Got it. Okay.
Okay.
So basically, they two different reactions on the same path, right?
Yes, exactly. It's different levels of oxidation.
Okay. Thank you.
You're welcome. Any other questions on that one? Okay, so last section in this chapter, which is what we've seen in many of our chapters now, is looking at these big picture. So looking at them with multi-step synthesis in mind. And the focus of this chapter is when we have two adjacent functional groups. So the idea here is that if we have two adjacent functional groups, specifically an alcohol and something that could have been a nucleophile, think epoxide. Because the idea here is if we react our epoxide with a nucleophile, then here's the two carbons of our epoxide. One of them will have an alcohol attached. The other one will have whatever nucleophile we've bonded to it, but they're on adjacent carbons. And so using an epoxide to get those two functional groups next to each other is really the easiest way to do that. So the book definitely goes into a bunch of examples for this. Let's see, I do have some practice ones or one practice one. Let me see, is that my last slide? Okay. I do have a second one. I just got to draw it out. So I have this practice one written out for us already. And then I have one more we'll do on the next slide. Just got to erase some stuff. So here's our first one. So let's take a little inventory. Both of them have a benzene ring. I don't think we've talked about this, but that's a symbol for a benzene ring. It's a nice one for note taking. If you can't just put that on the test as a benzene ring, but it's a nice one. And then we have a bromine. Over here, we have our benzene ring. We also now have a 3-carbon chain, and we have an alcohol group. So we have to be able to add 3 carbons onto this benzene ring and an alcohol. We don't know any benzene reactions, so this definitely limits us to what we can do. So with that bromine on there, though, we do know how to do a Grignard reaction. So with that bromine attached, we're going to do this. We're going to react this with magnesium in ether. And we're going to make a Grignard reagent. Because then we can react this with a lot of different things. But in order to get that 3 carbon chain and that alcohol attached, the best way to do this is to utilize an epoxide. So we're going to react this with an epoxide with a branch attached to it. So let me do a little numbering to show you where these carbons are coming from. 1, 2, 3. 1, 2, 3. So our Grignard reagent will bond to carbon number 1 because it's the least sterically hindered carbon, and we're using a strong nucleophile as our nucleophile. And so remember, our rule for that one is that it's only based on steric hindrance. So it will prefer primary over secondary. It will prefer secondary over tertiary. So we'll bond to that primary position. And then when we're using this, second step does need to be water. Oh, let me stay in my color coding here. So what we would get, let me give you a little mini mechanism here just to help you see what's happening. But we would do a nucleophilic attack. This would be our ring opening reaction that we talked about in this chapter. So our Grignard reagent is bonding to carbon number 1. Carbon number 2 will still be bonded to that oxygen and still be bonded to that methyl group. And then in that second step, when we add in the water, we would add a hydrogen to that oxygen to make it neutral. So actually that's our last step. I have my arrow stopping here, but really that's the only step that we would need. So remember, when we're adding on carbons, we really only know how to do that through 2 ways. So if we need to add carbons, we can do it with a triple bond terminal, react it with NaNH2, and then whatever carbon group we need to add on. So this was our alkylation of an alkyne. It does require an alkyne though, and we don't have an alkyne in this reaction. We could have added in an alkyne and done this. So we could have actually done it that way. And then option number 2 is to use some type of Grignard. So R with MgBr, and then we're either going to react this with a carbonyl or an epoxide, but that will give us those additional carbons as well. So those are our only 2 ways that we know how to add on carbons onto a chain. So we've talked about this either in lab or in lecture, a few times, but there's a couple types of reactions that should give you a little flag to say this has to be your starting point. Adding on a carbon is one of those. Removing a carbon is another one. So the big one here is ozonolysis. And then the other one that should send up a little flag that says you have to start in this way is if you're given an alkane to start with, no oxygens, no sulfurs, no halogens, no double bonds, no triple bonds, just an alkane, the reaction you have to start with is Br2 with lighter heat, and it will add a bromine onto the most substituted carbon. It's the only thing that we know how to do with just an alkane. So these are our three flags that are nice to have because they do give you a starting point. I know sometimes with these types of reactions, knowing where to start can be one of the most challenging parts of it. So when you see one of these scenarios, it's forcing you to go down a certain pathway. Okay, let's look at one more. Let me do a little erasing here though. And then I know I've said this before, so I'm going to sound like a broken record, but I'm going to say it again. If multi-step synthesis is something you struggle with, make sure you're looking at chapter 11. There's a lot of really good practice problems in there that utilize the chapters up until chapter 11. So they're really good. Okay, what about this one? We're starting with a 3-carbon chain. We still have a 3-carbon chain, but now we have a ketone. What are we going to do to that alkane?
Could we add H3O plus?
Cannot add H3O plus. What's the only reaction that we can do when we have an alkane? Oh, Br2 and heat. It is in the chat. Perfect. So Br2 with light or heat. That bromine is always going to add to our most substituted carbon. So there we go. So whether we wanted that bromine there or not, really, that's the only thing we can do with that first starting material, with that alkane. So now we have a leaving group attached though, so we can do different things. There's definitely going to be more than one pathway to take for this reaction. What would you like to do? What pathway do you see happening here? So I'm going to show you what I have down as my pathway for this. But there's definitely more than one way to do this. But I would do an elimination reaction. So we're just going to put in some base here. So that would give us our alkene. And now we can do H3O plus. And that is a Markovnikov reaction, which is what we want because we want the OH there. If we had an aldehyde on the end carbon, instead, we would need to use an anti-Markovnikov reaction. And then in our last step, we need to do one of our oxidation reactions. So we're going to go up here, and we know these from our last chapter, right? Not this chapter. Yeah, our last chapter. So we had a few different ways to do this one, but they were all the chromium-based ones. So the way that, or the one that I think sticks in my head always the fastest is PCC. So PCC with methylene chloride. Good. And then someone else in the chat said the sodium dichromate with H2SO4 definitely works as well. So yeah, This is definitely one way to do the reaction. Someone else in the chat said ozone. We don't want to use ozone because remember, ozone will cut one of our carbons off. So let me just grab a different color here. If we did ozone at this, oh, that is not a different color. If we did ozone at this point, we could make that, but we need one more carbon attached to it. So because we're not trying to lose any carbons, we don't want to do the ozone. Another way to do this would be if we did the Br2 reaction twice. And then did a double elimination. So we'd get an alkyne. So excess NaNH2, some water. Oh, sorry. And then acid and water, H3O plus, would get us to the ketone, because remember that actually makes the enol as like an intermediate product, and then it tautomerizes into the ketone. So let's see, 1, 2, 3, 4, 1, 2, 3, 4, oh, same number of steps. I originally also had it down in my notes as an epoxide reaction. 1, 2, 3, 4, 5, which is actually one more step. But we're kind of at the point where, because we have 13 chapters of reactions, there's definitely going to be a handful of ways to do these reactions and have them all be correct. Questions about either of the multi-step reactions or the pathway at all? Or anything really in general? Oh, we are finishing a little early. Okay, that is it. We are done with lecture. So we are finishing a little early. We'll start lab on time though, just because not every, well, I don't know, you guys are mostly here. Let's start lab early. So it is, what time is it? 9:57. Let's start lab at 10:05 just to give us a few minutes break to go stand up and stretch your legs a little. But we're going to do worksheet 13. So I'll hang out here for a couple more minutes just if there's any questions you have, but I will see you in lab in a few minutes.
Thank you.
Thank you guys.
Yeah.
Hi, Professor Henry. I have a few questions.
Yeah.
On chapter 12, when we're doing like the Grignard reagent, do we, on the test, do we have to do the first step, like the magnesium step?
It kind of depends on how the question is given to you. So like the one that we did up here, because we were given an alkyl halide and we wanted to turn it into a Grignard reagent, then we needed to do that step. But if you were given, let's see, let me just do a little erasing down here.
Okay.
If you were given a ketone and we wanted to make this, so we wanted to use like a methyl Grignard reagent, then that we could just write CH3 MgBr and water. That could be what we write in our box. So we don't need to show how that Grignard reagent formed because we're just adding it into the solution.
Perfect. And then is the ether optional or do we have to put it? Because I wrote it on my notes, but I didn't see it on like the arrow.
So ether, for this one, ether should not be an option. Ether should be required because it is the specific solvent that needs to be used here. It's not something that we have, it's not a flexible solvent, if that makes sense.
Yes.
Okay.
And then in the textbook problems, I know some of them, I don't know what it's called. Like it says like excess LAH and H2O.
Mhm.
Will it be excess on the exam or is that only because I know in other study guides, it was like common to see like, oh, this could be excess. So I'm not sure if I should be used to seeing it, or is it just something to like know?
I'm looking to, I have, so it's not, so are you thinking of like when it reacts with a carboxylic acid and an ester, like that reaction?
Yeah, because like it's not, I don't see like excess in the notes.
Yeah, so it's not really necessary to write down that it has to be excess because we can't stop it at just reacting one time. So like if we just used one equivalent of lithium aluminum hydride, we wouldn't get the product we want. We would get like a weird mixture of different things. So there's not like two separate reactions where there's just one equivalent and then there's another reaction where there's excess. There's just one reaction overall. Does that make sense?
Yeah, so the product would always, we would just always assume that there's multiple.
Yeah. So yeah, because we can't just react it one time,
Got it.
that's not an option. Putting the excess in there is maybe a little bit redundant because it's the only way we can react it.
Okay, thank you so much.
You're welcome. Any questions from the other couple of you in here?
I definitely do. Make it quick. So for a little disclaimer, I did not have to learn thiols and sulfides, so I better.
Oh, interesting. Okay.
Okay, so for reaction number 13, is a sulfide essentially just a catalyst?
Yeah, we could definitely call it that in this reaction.
Okay. That's kind of like, you're not really like you basically said you're not really using it. You're not really forming a product with it.
Yeah, I always think of it as that it's like the mediator. It's just helping these other two things get together.
Got it.
It's the
Okay.
matchmaker.
Okay, that makes sense. And then I think I was reviewing my notes from the last lecture, and there was something I was a little confused about. Let me pull it up. Actually, no, I got that one. Or actually, it was chapter 13, but just the first half.
Okay.
So when naming your ethers, is there generally like a certain number of carbons where you would name the chain as a parent chain?
No, I mean, really, any ether could be named using either one of these options. It's
Right.
just that when we treat the ether itself as the parent and just use the word ether, it's just easier to do that when each side is a little bit smaller or has very few branches. But really, you could do it with any ether and name and use either version to name it. It just kind of depends on when you're looking at it and trying to name it, which one
Right. So like
makes
that,
sense or which one's the easiest.
so like that bottom one, ethoxypentane, it
Mhm.
could also just be ethyl pentyl ether.
Yeah, exactly.
Got it. All right. And then I think there was one more. Okay. So it was one of the practice problems you had on after reaction number 3, acidic cleavage.
So they're gone now. Let me see if I have it in my notes. The box problems though.
I don't think they were box problems. It started with let me see, it was a tert butyl on one side and a propyl tert butyl ether reacted with HBr. You protonated the oxygen.
Mm-hmm.
The tert butyl was a leaving group. That tert butyl underwent an SN1 reaction. The Br acted as a nucleophile. You got that tertiary alkyl halide.
Mm-hmm.
But the other one for the So you were left with a 1, 2, 3 propanol. So then you protonate the oxygen, and the oxygen acts, well, then you basically have a water molecule that is able to leave. The
Right.
bromine acts. However, afterwards you had an arrow with propanol again. Was that maybe just a typo, or was that
Maybe. So whoops, let's do.
because it should have been an alkyl halide, another alkyl halide, right?
Yeah, it sounds like I had a typo because we would get this and then we would do this and then we'd have water off on the side. So I still had the water attached when I did it that way. Yeah,
Okay,
that was totally my
I guess I
fault.
was writing so fast that I forgot to ask that.
Oh, it happens.
No worries. Okay, I just wanted to verify that.
Okay.
I think that's really all I have for right now. So
Okay.
thank you so much. I'll see
You are
you.
welcome.
Wait, I don't think I'll see you again.
Yeah, that's right. This is the last one for us together.
All right. Well, I
But yeah,
guess
email me or text me if you need anything as our semester's ending.
sounds good.
Okay.
Thank you so much.
You are
Bye-bye.
welcome.
Have a good summer vacation.
You too. You too.